So in the first part of the experiment, we reviewed the concept of second-order systems, and the performance of control systems is divided into transient response and steady-state response. And in a second-order system, it is characterized by parameters such as the natural frequency, the damping ratio, and the damping frequency. The main goal here is for the system output to follow the input, and which we'll be checking using the step response. And in this part, I ran a MATLAB program where the damping factor is varied from 0 to 6. And when I've noticed that when the damping factor is small, the system has high oscillations and overshoots. But as you increase the damping factor, the oscillations seem to decrease until the system becomes more stable but more slower. But when the damping ratio is 0, the system becomes undamped and oscillates at a natural frequency. So here the damping frequency is varied while the damping factor is constant, and the damping frequency increasing basically changes the speed of the oscillations, and higher damping frequency or the higher damp frequency results in faster oscillations, and the system becomes quicker in terms of oscillatory behavior. And in this section, the transfer function here is 1 over 109 over s squared plus 6s plus 109. And from the calculations, I got these numbers, and from the graph, I got the overshoot, 39% overshoot. The peak time is 0.31 seconds, and the settling time is 1.3 seconds. And the theoretical and graphic values are close, which just shows that the formulas are also accurate. And here in this part, zeros were added at -4 and -100, also -1. And the observation here is that adding a 0 actually makes the system faster, but it also increases the overshoot. And if the 0 is closer to the origin, its effects gets stronger. So basically the zeros improve speed but also reduce stability. And here, additional poles were added again, and adding poles makes the system slower, though it also increases the settling time. And a pole from the origin, like -100, 100, actually has little effect, but a pole near the origin, in this case it's -1, actually greatly slows the system down. So basically the poles reduce responsiveness depending on their positions in the graph. So in summary, I performed the simulations of second-order systems using MATLAB by varying damping factor, damp frequency, and adding poles and zeros. And the outputs here showed how these parameters affect the overshoot and the speed of the response, also the stability of the system. As for the challenges, one challenge I experienced was understanding how the parameters worked, or what are the parameters and how they are related, since they are interconnected in the formulas. And another difficulty was interpreting the graphs as well, because especially identifying overshooting and settling time accurately. Also, one last was modifying the MATLAB code correctly, especially when adding the poles and zeros were here. This actually required more attention. And my takeaways in this experiment are: number one is increasing the damping actually reduces the oscillations, but that actually also slows the system. Two is that zeros, in terms of zeros, zeros make the system faster, but it also increases overshoot. And as for the poles, poles slow down the system, especially when it's near the origin. And so overall, the positions of poles and zeros actually affect system behavior. So they must be really carefully designed. And that's it for this reaction video.